Good morning, dear students. Today we are having the 17th practical lesson about numerical series. So actually, the rest of practical lessons are about different kinds of series, and today we will start with the numerical series, and we will investigate series for convergency. And first of all, we will calculate the sum of the series. Actually, what is series? It is in infinite sum. And for numeric series, it looks like this. So it can start from 1 and so to infinity, and a n, or maybe un, so different. So these are coefficients of this series. And what about the first series? So 1, let's write it down, 1 by 1 over 1 by 3 plus the next 1 over 3 by 5 plus 1 over 5 by 7 and yeah, so how to write it down? So how to find the nth term? Actually, we can see that let's just look at denominators. We have odd numbers, and the first multiplier is less than second by 2. So let's write it like this. So 1 over 2n minus 1 by 2n plus 1. So this is the sum of this. So this is how the series looks like. So let us write down the nth term. So it will look like this. And now let's expand it to simple fractions with the using method of undefined coefficients. Let's expand brackets and regroup coefficients. So 2an plus a plus 2bn minus b. Okay, and let's write down the system. So 2a plus 2b equals 0, and a minus b equals 1. So from this system, we can find that so a equals minus b. So from this equation, so 2a equals 1. Then a equals 1 over 2, and b equals minus 1 over 2. So un will be equal the following expression. So here will be 1, 1, here will be minus, and denominator is multiplied by 2. And let's rewrite the series. So we can move out 1 over 2. Out of brackets. So done with it. And actually, what is so we need to find the partial sum over the term. So it looks like this. So the sum over the of n first terms. So k from starting from 1 to n. And yeah, actually, let's do like this. So k starting from 1 to n, and here to k minus 1 to k plus 1. So now we will find this partial sum. So let's do it. So for the first term, 1 over 1 minus 1 over 3 plus 1 over 3 minus 1 over 5 plus 1 over, let me write down brackets, 1 over 5 minus 1 over 7. And continuing calculating. So now let's continue. So to the nth term. So writing it down. So having such expression, and let us write down previous. So 2n minus 3 and 2n minus 1. So actually, what can we see here? That some members are eliminated. So how they are eliminated? So minus 1 over 3, 1 over 3, minus 1 over 5, y, 1 over 5, and so on. So here, minus 1 over 2n minus 1 plus 1 over 2n minus 1. So finally, we will receive the following expression. 1 over 2 and 1 plus 1 minus 1 over 2n plus 1. So this is the partial sum. And how to calculate the sum of the series? We will have to calculate the limit of this partial sum. So this. And what can we see? That this expression approaches 0, so the sum will be 1 over 2. So this is the partial sum of the series. Oh, so this is the sum of the series. And as we could find this sum, it is finite, so we will write down that series converges. So this is the final solution. Any questions about this exercise? Okay, if no questions, let's move next. So now moving to 1b. So we have the following series. Arctangents of 1 over 2 plus arctangents of 1 over 8 plus arctangents of 1 over 2n square, and so on. So how to calculate sum of such series? So let's try the method of mathematical induction. I guess you know this method. Let me remind it you. So we will calculate a partial sum for first 3 or 4 terms, and then we will calculate the nth partial sum. So the S1 equals just the first term. And what about S2? So it equals the following expression. And we will use the following formula. So arctangents of x plus arctangents of y equals arctangents of x plus y and 1 minus xy. Let me check here. Yeah, so actually, yeah. So we will use such formula. So here is arctangents of 1 over 2 plus 1 over 8 and 1 minus 1 over 2 by 1 over 8. So in the numerator, what do we have? So 5 over 8, and here, so 15 over 16. And it will be equal 2 over 3. Then, what about S3? So let's calculate it. So it will be S2 plus the next term. So 1 over 2n square. So it will be 1 over 18. So again, using this formula, so arctangents of so 2 over 3 plus 1 over 18, and here 1 minus 2 over 3 by 1 over 18. So what about the numerator? So 6, yeah, so multiplying by 6 this part, so 13 over 18. And here, so it will be equal 1 over 97, so 26 over 27. And if we simplify it, we will see that it will be equal. Okay, so let's simplify it one by one. So 1, 2, and here dividing. So dividing by 3. So dividing by 9. Here will be 2, and here will be 3. And it will be equal arctangents of 3 over 4. So have you noticed some rule maybe for these partial sums? So looking at the first, the second, and the third. Or you need to calculate one more.
I think that numerator with each term, numerator increases by 1 and denominator also.
Yes. So let's suppose that Sn will be equal n over n plus 1. But we need to, arctangents of this expression, of course. But we need to prove it. So we have to calculate Sn plus 1. So this is the idea of mathematical induction method. So we need to prove for n plus 1, and after that, so we will see that so for Sn it is true. So let's do it. So arctangents of this expression plus arctangents of this, and let me write down n plus 1 square. So we will again use such formula. So add in this expression and this expression, and 1 minus n by 2 n plus 1 cube. So let's simplify it. Let's try to simplify it somehow. So what do we have here? So this expression minus n. So finding the common denominator. So 2n by n plus 1. And actually, yeah, so again, received the common denominator here. So next. Next, let's cancel these parts. And continue simplifying. So so what we will receive n plus 1 by this expression, and this is the denominator. Okay, let me check my notes. We will not calculate everything here, but let's check that we are on the right way. Just to check this. Yeah, correct. And finally, after whole transformations, we will receive arctangents of n plus 1 over n plus 2. So it means that formula for Sn is correct. So this is the partial sum. And how to calculate the sum of the series? We will just calculate the limit of the partial sum. So actually it will be arctangents over 1, and it equals p over 4. And as we calculated the sum, so it means that series converges. Any questions about this exercise? Okay, if no questions, let's solve one more exercise with calculating sums of series. So 1C, one more interesting case. So we have the following series. By the way, what about hotkeys? So Control T, S. Okay, so n from 1 to infinity. And we have the following series: 3 in power of n plus 2 in power of n, and divided by 6 in power of n. So, how to solve this exercise? As you noticed, we can split this series into sum of two series, so separately. So what we will have, so the following series. And if I continue simplifying, so I will receive 1 over 2 in power of n, and here will be 1 over 3 in power of n. So done with it. So let's look at each series separately. So writing down the first series. So 1 over 2 plus 1 over 4 plus 1 over 8 plus 1 over 16 and so on. So what do you see here? Actually, it's a geometrical progression. So the first term is 1 over 2. Yeah, and by the way, this is the geometrical progression that infinitely decreases. So the first term is 1 over 2, and the denominator of such geometry progression is 1 over 2. So by the way, this is a geometrical series. So it converges when when the denominator is less than 1. So it converges. But let's, of course, calculate the sum. So sum of the first series, let me use such index, upper index. And it will be equal a minus 1 over q. So this is the formula of infinite, so a1. So the first term, so it will be equal, so this is the formula of infinitely decreasing geometrical progression. So 1 over 2 minus over 1 minus 1 over 2. So it will be equal 1. Let me check here. Of course, yeah, so it equals 1. Okay, everything is correct. And now let's look at the second series. So actually the same story: 1 over 3 plus 1 over 9 plus 1 over 27 plus 1 over 81 and so on. So we have again the geometric series. So the first term is 1 over 3, and q equals, so the denominator equals 1 over 3. It is less than 1, so the series converges as well. And let's calculate the second sum. A sum of the second series. So again, using the following formula. So 1 minus q. So 1 over 3. And 1 minus 1 over 3. So 1 over 3 by 2 over 2 over 3. And the answer will be just a moment. The answer will be 1 over 2. So finally, the sum of the series will be equal sum of this subseries. So S1, S equals S1 plus S2. So 1 plus 1 over 2, and it equals 3 over 2. So any questions about this exercise? Yeah, and by the way, the series converges. So any questions? I guess that no questions. So done with this, and now let's switch to the exercise 2. Now we will investigate series. So we will investigate convergence of the series. So we're using different kinds of tests. So firstly, we have so the following series. So n. Okay, let me zoom it in. So do you see well all this series?
Yeah, we can see it.
Okay, if you can see, that's great. So the following series. So n 1 over square root of n squared plus 2n. So we will use the comparison test. We will compare with so the nth term will be compared with so we will compare this series with this harmonic series that divergent. So what can we say about this series? So actually it is so when n approaches infinity, it is equivalent to so let's use so 1 over n square, and it equals 1 over n. So it is equivalent to the nth term of the divergent harmonic series. So it is always divergent. We know we know about it, and it means that initial series diverges as well. So any questions about this exercise? Okay, if no questions, let's move next. So then we will have another series. So in 2b. So n plus 1 over 3n 3n cube minus 2n. So un is the following, and we will compare it with the generalized harmonic series. So actually the nth term is equivalent, so when n approaches infinity, it is equivalent to 1 over 3n square, and we will so we will compare it with this series. So 1 over n square. So for this series, this degree, so generalized So in this case, for generalized harmonic series, this degree p equals 2. So and it means so it is greater than 1. So it means that this series is convergent. And as our term is actually has the same order of so the same order as the nth term over this series, it means that initial series is convergent as well. Any questions? Okay. No questions. So now let's move to the next exercise. So, writing down the yeah, to see, by the way. So writing down the series, so 5n square plus 1 over 7n square minus 4. Okay, so un equals, so the nth term is the following. And uh, uh, so let us look at this nth term, and we can see that it is probably so the limit of the nth term when n approaches infinity, it seems not be equal to 0. So we will use divergency test. So calculating this limit, and we will see we will receive 5 over 7, and it is not equal to 0. So actually this is the divergence test. So according to it, we can see that this series is divergent. And for convergent series, yeah, so for the series to be convergent, the limit of nth term must be equal to 0, but it is not. Any questions about this exercise? Okay, no questions, so solve in 2D. So the following series, so 1 over n by square root of n plus 1 minus square root of n minus 1. Let's write down the nth term. So let's transform it a little bit. So we will multiply this multiply and divide this series by conjugate. This term, sorry, not series. So here will be plus, here minus, and plus. So now expanding these brackets. And what I have in the numerator. So n plus 1 minus n minus 1. So continuing simplifying it. So here I will receive 2 over this expression. So n is eliminated, but 1 is not. And when n approaches infinity, this expression will be equivalent to n over, so this expression will be equivalent to 2 square roots of n. So 1 over n square root of n. So let's write down the generalized harmonic series. So n equals 1, so to infinity, and the following series. So if we rewrite it, I will receive here, so n in power of 3/2. And we can see that this power p equals 3/2, and it is greater than 1. So this generalized harmonic series converges. And it means that initial series converges as well, according to comparison test. Any questions about this exercise? Okay, if no questions, let's move next. So the following exercise E. So we have the following series: sine of p over 2 in power of n. And so writing down this series. So when n approaches infinity, so this argument of the sine approaches 0. So as we remember, when argument of sine approaches in 0, okay, let me write down. So when x approaches 0, so sine of x is equivalent to x. So this sine will be equivalent to its argument. So equivalent to this term. So p over 2 in power of n. And we will compare it with the geometric series. So with this, so 1/2 in power of n. So actually, yeah, as it is, so this series is convergent because, so as harmonic series, or not harmonic, a geometrical series, which has a denominator q equal 1/2, that is less than 1. So this series is convergent. It means that the initial series is convergent as well. Any questions about this exercise? Okay, no questions. So moving to the next exercise. So 2F. Okay, so here we will use D'Alembert test. Let me remind you how to use it. So we will calculate the following limit. So un plus 1 over un. Okay, let me check. Sometimes I confuse them. Yeah, so un plus 1 divided by un. So we will calculate the following limit. So then, if c is less than 1, the series is convergent. if C equals if C is greater than 1, divergent. And if C equals 1, we cannot say if it is convergent or divergent. So we will have to provide more investigation. So it is unknown. So to use we will have to use other tests. So let's have practice with such test, Downberg test. So writing down the series. So 3n plus 1 factorial over 8 in power of n and n square by n square. So the nth term is the following. And what about n plus first term? So n plus 1. So we have the following term. So 3, let me write down in detail. So n plus 1. Here will be n plus 1 and n plus 1 square. So it will be equal. So let me expand brackets. So 3n plus 4 factorial. And this remains without changes. So un, yeah, so un plus 1. Okay. So now calculating the limit. So it will be equal. So this expression, and we will multiply by this fraction, but let's turn it over, of course. So now let's simplify it. So first of all, 8 in power of n, and here just 8. So actually we will move a 1 over 8 out of brackets. Then n square and n plus 1 square are equivalent. And now expanding this expression for factorial. The numerator will be written like this. So 3n plus 1 factorial by 3n plus 2 by 3n plus 3 by 3n plus 4. So we will receive the following limit. So it will be equal to plus infinity. So it will be infinite limit. So it, of course, it's greater than 1. So it means that the initial series is divergent according to Downberg test. Then, so okay. So any questions about this exercise? Okay, if no questions, let's move next. So 2G. So we will have more practice with D'Alembert test. So the following series. So n equals 1. So to infinity. Yeah, we will have a break after we finish task 2. And then we will have a break. So 2 by 5 by, yeah, and so on. 3n minus 1. And here, so 1 by 5 and so on by 4n minus 3. So writing down the nth term. So this is the nth term, and what about n plus 1? So it will be multiplied by 3 n plus 1 minus 1. And here 4 by n plus 1 minus 3. So rewriting it. So simplifying. So here we'll have 3n plus 2. And here 4n plus 1. So done with it. So now let's calculate the limit. So u plus n and divided by un. So swapping numerator and denominator. Actually, what we can cancel here. So what will remain? So 3n plus 2 over 4n plus 1. And this limit will be equal 3 over 4. And it is greater than 1. So it means that initial series is convergent. Any questions about this exercise? Okay, I guess that no questions, so moving to the next. So 2h. One more exercise for D'Alembert test, then we will use other test. So n by tangents over p over 2 in power of n plus 1. So un equals n by tangents, and what about un plus 1? It equals n plus 1 tangents over p over 2 n plus 2. 2n in power of n plus 2. So calculating the limit. So the limit will be the following. Okay, but let me write it down like this. In this case. So first of all, yeah, by the way, let's first of all cancel n and n plus 1 because they're equivalent when n approaches infinity. And what about tangents? So n approaches infinity, and the argument of tangents approaches 0. And the same story for sine. So when x approaches, argument of tangents approaches infinity. Tangents of x is equivalent to x. So I will replace, so I will just remove tangents and replace with the arguments. So now canceling P, canceling 2. So actually we will have this, so 1/2. It is less than 1, so the initial series is convergent. Any questions about this exercise? Okay, I guess that no questions. So now moving to the next exercise. We will use another test. Radical Cauchy test. First of all, I will write it down. So we will calculate the following limit. So when n approaches infinity, the root of power of n for the nth term. And again, so the conclusions from Darmstadt test are the same as for radical Cauchy test. So if this limit equal less than 1, the series is convergent. If greater than 1, divergent. If it equals 1, so we cannot say if it convergent or divergent. So we will have to use other kinds of test. And for next couple of exercises, this radical Cauchy test really so a good solution to investigate. So good approach. So let me write down the series. Yeah, so this is 2i, so 2n plus 1. And this expression is in power of n. So the nth term is the following. So C will be equal, yeah, so this limit, and we will calculate, so limit of this, so such limit. So we can already simplify it, so n, 1/n, so we have the following expression. And yeah, we can even remove brackets. So we can see that this limit equals 1/2, and it is less than 1. So this series is convergent. Any questions about this exercise? Okay, if no questions, let's move next. Where it is? So 3 and 2j. So the following series 1/3 in power of n, and multiplied by the following expression. So 1 plus 1/n and in power of n square. So writing down the nth term and calculating the limit of this nth term. And what we will receive. So first of all, let's move 1/3 out of limit. Then I will receive 1 plus 1 in power of n. So 1 plus 1 over n in power of n, and it will be equal to number e. So this is the second perfect limit. So this limit is equal to e. So this limit, and the final answer e over 3, and it is less than 1. So the initial series is convergent. More question? Any questions? Okay, I guess that no questions. So let's solve a couple of exercises and we will have a break. So now 2k. So we're having the following series. So n plus 1 and logarithm in power of 2 over n plus 1. So having the following term, nth term, and here we will not use a radical Cauchy test, we will use integral Cauchy test. I will not write it down here. So actually the idea is the following. We will calculate the integral. So the first limit will be so we will calculate the integral of these terms. So we will calculate the integral where the integrand will be the nth term. And how to define limits? So the lower limit will be, bottom limit will be equal 1. So according to the index, so will be equal to the index of this sum. And the top limit equals to the, so upper limit equals to the upper index, so infinity in our case. So we have the following integral. So dx over x plus 1 and multiplied by logarithm square over x plus 1. So the idea of the integral Cauchy test, so if the integral is convergent, it means that the series is convergent as well. If the integral is divergent, the series is divergent. So here we see the differential of the logarithm. So dx over this expression is differential of the logarithm. And we have 1 over a logarithm of x plus 1. And with the substitutions from 1 to plus infinity. So, substituting infinity, we will receive 0. If I substitute 1, I will receive 1 over logarithm of 2. So it is integral is convergent. So it means that series is convergent as well. Any questions about this exercise? Okay, if no questions, so let's solve one more example, one more exercise, and after that we will have a break. So, the following series, 1 over root of power of 4, 4n plus 5, and in power of 3. So the nth term is the following, and calculating the integral. So from 1 to plus infinity. Okay, so let me write it down like this. So 3/4. Then, so using differential sign, so differential entry technique. Uh, then, okay, so having the following the following antiderivative, so it will be so root of power of 4, and yeah, multiplied by 4. So actually, and oh, stop just a moment. Let me check it here. So the yeah, so correct. So this integral will be divergent. So if I substitute infinity plus infinity, we will receive plus infinity. So this integral is divergent. So it means that the initial series is divergent as well. Any questions about this exercise? Okay, if no questions, let's have a break for 5 minutes, and then we will continue. So we will investigate uh, series with the change in signs. Okay. Okay, let's continue. So now we have the following. Okay, let me share my screen. So we will have the following series. So task number 3. So we have to investigate the absolute and conditional convergence of given numerical series of alternating signs. So writing down the following series. So we will start investigating the modules of this signs of the series. So of terms. So for 3a. So we have the following series: cosine of n by n cube. So we can see that cosine always changes its sign. And now let's look at the series of with the which is formed by modules. So actually n is always positive, so we can just write down like this. And what can we say about such series? So about this term. So it equals module of cosine of n over n cube, and it is less than 1 over n cube. So because cosine is always greater or no, or always less or equals 1. So we can write down like this. And what about the following series? So n from 1 to infinity and 1 over n cube. So we have the following series, and actually what can we say about it? That it is convergent. So the uh, power equals 3 and it is greater than 1. So this generalized harmonic series is convergent. So it means that this series is convergent. So this series converges. And it means that the initial series converges absolutely. So because of modules. Any questions about this exercise? Okay, I guess that no questions. So, moving to the next exercise 3b. So here we have alternating series. So it means that signs of this series are so changing just so 1 through 1. So what does it mean? So for example, if I choose n equal 1, so it will be equal 1. So we will have plus. If n equals 2, so it equals minus 1. N equals 3, we have 1. So always, these signs are alternating. So it means that, such series are called alternating series. So what are we doing next? So let's check, let's investigate, let's start investigating modules. So un equals this expression, and un plus 1, so we will use here D'Alembert test. So n and so n plus 1, and here 5 in power of n plus 1. So calculating the limit. So when n approaches infinity, so n and n plus 1 are equal, so just cancel them. And here I receive 1 over 5. So it is less than 1. So it means that this series, so series of modules, it looks like this. It converges. And the initial series converges absolutely. Any questions? Okay. If no questions, let's move next. So we will have the following series. So minus 1 in power of n and 1 over square root of n. Here we will use the Leibniz test. So how it works? So let's write down un. Yeah, first of all, we will have to calculate. So Leibniz test so has the following. Okay, I don't remember how the Leibniz, yeah, so correctly, Leibniz test. So the this surname. So we have two conditions must be. So we have to meet two conditions. So first of all, that limit of un, so of the module of this term, must be 0, and the sequence so is decreasing. So if so, the series is convergent. So writing down. So first of all, calculating the limit. So such limit un. Sorry, not root of power of n. So we are having the following limit. So and so it will. So it equals so one limit of 1 over square root of n, and it equals 0. So the first condition is fulfilled. Then what about the decreasing? So let's write down un. So un equals 1 over n. And what about un plus 1? It will be equal 1 over n plus 1. And what can we say? So how can we compare? So 1 over square root of n is greater than 1 over 1 of square root of n plus 1. So the sequence is decreasing. So it means that series converges according to Leibniz test. But let's look at series that formed by modules. So we have the generalized harmonic series. And what can we say about this harmonic series? So it has a power of 1 over 2. And so this power of 1 over 2 is, so P equals 1 over 2. It is less than 1. So this generalized harmonic series diverges. And as the series based on modules is divergent, it means that initial series converges conditionally. So you actually can start with, so if you are sure that the series is convergent, so when doing your individual tasks, tests, and so on, so if you see that the series must converge absolutely, so you can start investigate modules. But if you see that the series are so that series of modules are divergent, you also will have to use the Leibniz test. Here we just started, so here we started with using Leibniz test, and after that investigated the series of modules, and uh, we concluded that the series converges conditionally. Any questions about this exercise? Okay, if no questions, let's solve the last exercise. So, uh, so minus 1 in power of n by 2n plus 1 over 3n plus 2. So let's calculate the limit of the nth term. We will see that it is equal, so limit, of course, don't use limit sign. So it equals 2 over 3. And it is not equal to 0. So it means that we don't have to continue investigation, and we can conclude that the series is divergent. Any questions about this exercise? About the whole lesson? About previous lessons? Okay.
Sorry, I do have a question about home tasks.
Individual home task,
Uh,
right?
yeah, that's correct. In the task 3, we are asked to solve the inhomogeneous differential equation with constant coefficients using the method of variation of an arbitrary constant. It's like when we say that those constants C, they are like functions, right?
Yes, yes. So according
Uh-huh.
to this, so where was this exercise? Yeah, so according to the last exercise of the 15th practical lesson. So yeah, you assign C1 and C2 as functions.
Okay.
Okay. More questions?
Uh,
Okay. Uh, if no questions,